All right, so here we are, predicates and quantifiers. What is that? What's it all about? What's it mean? So we're going to look at predicate logic today, quantifiers, what that's all about. There's three different types that we care about. What is a universe of discourse or domains? Scope, which since we all have 1410 background, we know about scope, variable scope. We're going to talk about that. And then looking at nested quantifiers, okay? All right, first up, let's take a look at a couple things here. On the first day, we talked about some examples of, I think I had something like x plus 1 equals 7 or whatever. Is that a proposition? And the answer was what? No. It's not. Why wasn't it a proposition? We didn't have enough details. Well, with predicate logic, we can actually handle situations like that. So at the moment, these are not propositions, but we can make them into propositions, okay? So we can start out by saying something like this. Let P of x be the statement x is greater than 3. And P of x is, if you remember our algebra, right? That's a fancy f of x there. That's supposed to be an f, right? You remember this, right? We know about this. This is all we're talking about. It's just that kind of a function, okay? So we're going to say let P of x denote this statement here. So then what is the truth value of P of 4? True, because 4 is greater than 3. What's the truth value of P of 2? False, right? Because it's not greater than 3. Pretty simple. That's the basic idea of a predicate, okay? So let's look at a little bit more complex one. Let A of x denote the statement that computer X is under attack by an intruder. Suppose that of the computers on campus, only CS2 and Math 1 are currently under attack by intruders. What are the truth values of the following statements? What's the truth value of that one? As far as we know, it seems false based on the information we have, right? Truth value of this one? True, because we know that one's under attack. And the truth value of this one? True. Okay. Again, super simple, straightforward. We're going to build, though. Just want to make sure we have the foundation here, okay? So here's one where we're using two variables in our predicate, in our function. So let Q of x be the statement x is equal to 3 plus, or equal to y plus 3. So what's the truth value of that? Right? We just plug in the 1 for x and the 2 for y. And the reason we're plugging them in that order is why? Because this function says so, right? If that function were written like this, then we do it differently, right? But we plugged it in that way, and we see that 1 is not equal to 2 plus 3, so this one is false. What about Q of 3, 0? 0, okay, or is true, right, if we do the math. Okay. So here's a little bit more involved one, and we're going to bounce back and forth between mathematical ones and English structured type ones just to get our heads wrapped around this. And I know I'm going pretty quickly on this part because this part should be pretty easy for you guys, I think. So let's look at this next one. We're going to use A of C, and it's going to be the statement that computer C is connected to network N, right? Where C is a variable that represents a computer and N is a variable that represents a network. Easy enough. So let's say that we know that Math 1 is connected to network campus 2, but not to campus 1. What are the truth values of this and this? So the first one is false. Yep, it's not connected to campus 1. Second one? True. Okay. So hopefully you can see these are pretty easy to read, right? Until we get more involved a little bit. It'll be a little trickier, right? Here's one with 3 variables. You can have as many as you want, okay? R of x, y, z, and that is how you pronounce that, is the statement x plus y equals z. Okay, so what are the truth values of these two statements? So basically we're saying is 1 plus 2 equal to 3. First one, true. Is 0 plus 0 equal to 1? False, right? Okay, good. And this is another way you can express this. We have up here R, but it could be a P or whatever. But what we're saying is that you can have P of some variable 1, 2, 3, all the way up to an n number of variables. There's no limit to how many variables you can have, okay? So it's totally legitimate if you want to have an X and a Y and a Z and an A and an F and so on and so forth, okay? Yeah.
Does it have to be bounded? We couldn't let n just go off to infinity?
No, it can't, well, you can't be infinite just for the fact that how could you calculate it if it were infinite, right? So it can go up to n number, which can be anything that's countable, right? Yeah. So it could be 100 variables, which is kind of crazy, but you could certainly do that, yeah. All right, now, we've seen this kind of stuff before, right? This is programming code right here. Regardless of the language you speak, unless it's Python, you probably recognize this, right? Python's a little bit different in the syntax, but it's pretty close, okay? So what do we have here? We're having this thing here, if x is greater than 0, then do that, right? That's going to increment it by 1. Well, this is the same idea. This right here acts like a function, and typically it is a function. You're passing in a variable into a function or into a method, and you do something with that variable, okay? So when we have a function that's something like, we'll just call it some function, some parameter, and some code here, this is the same idea, right? This is p of x, right? It's some f of some value, right? So let's make it a little bit more realistic. What if I had a function that said add, and it's going to add x and y? You could pronounce that add of xy, right? That's the function name. And in here we have our code that's going to add those two numbers together. So this is not a new concept. This is, if you have your Algebra 2 background, you should be familiar with this, with just our typical, what's a function f of x. But also with our programming background, you should be familiar with this, okay? Questions? All right, so consider, let's take a look at p of x. What are the possible values of x? Yeah, we have to decide that. We have to determine that. Okay, that idea, we call that the domain, or the domain of discourse, or the universe of discourse. Those are all meaning the same thing, right? And when we get into set theory in a couple weeks, we'll see this a little bit more in depth. But this is, the domain is every possible value that x could be. So I could simply say that the only values of x that are being allowed to be plugged into there are, it can either be 1 or 2 or 3. That's all that's allowed to be plugged in there, okay? So that would be, the domain of x would be 1 through 3, okay? Well, when we want to refer to this, the domain, we use these quantifiers. I'm going to show you what they look like in a minute. But you can refer to a specific amount of the values in the domain. So again, let's say that our domain is just simply 1, 2, and 3. Those are the only values we care about for whatever reason. I can use a quantifier, which is a little symbol I'll show you in a minute, to determine if we're talking about all of those or some of those, okay? So this one right here is called the universal quantifier. It's like an upside down letter A. What this means, if I write it in an equation, that's how you would see it. This means for all values of x in the domain of x, whatever that domain might be, p of x is true. That's what that is now a proposition, by the way. I'm proposing that for all values of x, p of x is true. Dig it? Okay? This is the existential operator. It's a little backwards E. And again, you'd see it look something like this. And again, we have some limited domain. Let's just go with the numbers 1, 2, and 3 again. It doesn't even matter what p of x is at the moment. I'm just making the claim that this is how you pronounce this, there exists some value x from the domain of x such that p of x is true. Okay? That's how you pronounce that. We're going to look at some actual examples in a moment. Basic idea makes some sense? Okay? These are just notation for how to write this stuff, which comes in handy when we get to the proofs. All right? Next up, we have that should not say existential. That's supposed to say uniqueness. That is the uniqueness operator. This is nice. I don't have to actually edit the slide. I can just leave it like that and post it this way. That's the uniqueness operator, okay? And it's just the existential operator with a little exclamation point. And what that means is, again, if we write it out, that means there exists, and then an X there. There exists exactly one value of X from the domain of X such that P of X is true.
We throw the domain in, so we have like little weird shape. Is that?
We're gonna, we're gonna get to how you represent the domain in just a minute. That's a good point, though. Yeah, because right now I've just said there's some domain out there that's got some values. I haven't really shown you what that looks like. We'll do that in a minute. And apparently I got existential here too. That is uniqueness. Okay. So again, I just wrote this a second ago, but this is a table that's right in your book. I thought I'd show it here for you guys. This statement means that P of X is true for every single value of X. And that's when this statement will be true. This statement will be false if there's just even one P of X that's false. If one value of X that's false, then the whole thing is false. Because this whole point of this operator is I'm saying all of them are true. Okay? And again, this will make a little bit more sense when we get some concrete examples. The one below here, we're simply saying there is an X for which P of X is true. So if my domain is the numbers 1, 2, and 3, and I'm plugging in those values into my P of X formula, as long as one of those is true, maybe we were having that thing a minute ago where it's X plus Y equals, or X plus 1 equals 3 or whatever. If we plug in one of those and it's true, then this is true. But if all of those are false, then this formula here is false. Okay? What's that?
You said if all of them are false, there's false, if all of them are true, then it's also false, right?
No. So that's a good question. His question was, if they're all true, would this also be considered false? And the answer is no. If they're all true, then at least one of them is true, right? So the existential is saying at least one is true. Now, if we're talking about the uniqueness quantifier, this one, then if they're all true, then with the uniqueness quantifier, if they're all true, then that one would be false. But with just the existential, all of them being true, they're also at least one is true. Okay? Good question. Other questions? I just do that to remind me to ask you guys. Otherwise, I'll forget. Okay. So here we go. We've got some examples here. So let P of X be the statement X plus 1 is greater than X. What is the truth value of this quantification? Very good. It's a trick question. What's the domain? Now, if you've been in my classes before, you know I don't do trick questions on your homework, but I will do them in class because I want to get you guys thinking. If I do it on your homework, that's just me setting you up to fail. That's not cool. But in class, I will do trick questions. When you see this, you cannot answer it because we don't know the domain. Now that we have the domain, the question is, what's the truth value of the quantification universal X, P of X, where the domain consists of all real numbers? I heard some falses and trues. So the first question is, what's a real number? Right? When we get into set theory, we'll talk about what that is in depth. We're going to talk about different types of numbers. But for now, let's take a look. Who said true? All right, who says false? Who says I don't care? Better be nobody that says that. The answer is true, okay? Real numbers are positive, okay? They're also negative. Why is that true? Yeah. So rather than numbers, so let's take a negative. Negative 2. If I add 1 to that, so that negative 2 is X. If I add 1 to that, I get negative 1. Is negative 1 greater than negative 2?
Yes.
Is it? I heard somebody say no.
Yes, it is bigger.
It is bigger, yes. Yes, okay, it is bigger. Okay, so this is true for all real numbers. Okay, real numbers are positive and negative, and so that will. I think it's easy to see that with a positive number, but that's also true with negative numbers. Okay. All right. Questions on that idea? Let's look at another one. Let Q of x be a statement x is less than 2. What is the truth value of the quantification for all x Q of x where the domain consists of all real numbers? False. Good. Because that's saying that all real numbers are less than 2. And that's definitely not true. I can think of 1, 3. That's not less than 2, right? Okay. Easy enough. Again, baby steps till we get to the bigger stuff. But this is the foundation of proofs, these ideas here. Okay. Let P of x, let P of x is, how about let P of x equal? Let P of x equal x squared is greater than 0. All right. What is the truth value of that where we're talking about all integers? Ooh. So I'm hearing people saying point this, point that. Look, everybody look on the screen here. Integers. So integers are not decimals, right? So one example we had was 0. I heard somebody say 0. Okay, we'll leave that one out for a minute. If ignoring 0, is this true? Yeah, because any negative number squared is greater than is positive, right? And any positive number squared is also greater than 0. And to be honest, I don't remember if I was thinking about 0 when I did this. I think that I might have wanted this to be less than or equal, or greater than or equal. Let's see. Oh, I didn't give the answer. Yeah, it's false. Okay, because of the fact that 0 is in that group, all right? All right, so notice this is important. And this is a critical thing to understand, and you will be asked this on your homework for sure. For all x, P of x is the same thing as the conjunction of x1, x2, x3. So look at our domain of discourse at the moment as integers, okay? That's a big number. That's infinite, negative infinity to positive infinity, all whole numbers. Let's make a smaller domain for a moment. The domain is just the numbers 1, 2, and 3, okay? That's our domain at the moment. Well, if I'm saying this is true, back. If I'm saying that's true, then I'm saying that P of x is true, and P of that x is true, and P of that x is true. I'm saying all of them are true. Okay, so that the universal quantifier is the same thing as the conjunction of everything in the domain being passed into the function. Follow that? What we just did here is actually a proof. This is a very specific type of proof. It's called a proof by counterexample. We simply found one example that proved that this statement was not true. So this statement is false because there's just one single event where it wasn't true. And that event was when it's 0. Okay? So that's a proof by counterexample. That's an actual legitimate proof technique. If you can just find one example that proves your proof wrong, you're done with the proof. You don't have to go any further. Oftentimes you can't find it and you have to keep going, right? But that's the idea. All right, here's another one. Now we have a nice small domain. What's the truth value of this? Where P of x is x squared is less than 10. And the domain is positive integers not exceeding 4. So what's our domain? Yeah, 1, 2, 3, well, yeah, 1, 2, 3, 4. Your brackets are supposed to look like Alfred Hitchcock, but my one on the left looks like Barney from The Simpsons. That's what I see when I look at it. Okay, that's our domain right there, all right? So, in other words, we're saying that P of 1 is true, P of 2 is true, P of 3 is true, and P of 4 is true. That is what we're claiming. That is my proposition, right? I'm proposing that to be true. Okay? Is it true?
No.
It is not. Why is it not true?
4 squared is greater than 10.
Yep, that's 16 right there. Okay? Everybody see that? We good with that? Okay. Answer's false. We're good there. All right. Here we go. Using some English stuff instead of math. What does this statement here mean? All right. If n of x means that a computer x is connected to the network and the domain consists of all computers on campus. So what does this mean, Beck? Can you give us a shot at this?
That all the computers are connected to the network?
That's right. All computers on campus. That's our domain, campus. Right? For every computer X on campus, computer X is connected to the network. That's sort of the nerdy math way to say that, right? That's a very literal translation. But if we want to get to a little bit more human language, we'd say every computer on campus is connected to the network. Okay? How are we feeling so far? I promise I'll make it harder. Okay. Let's look at the existential quantifier. We briefly saw it a minute ago. Here we go. This means there exists an x such that P of x is true. That is the way you pronounce that. Okay? So let's start with this. Let P of x denote the statement that x is greater than 3. What is the truth value of the quantification of that, Scott? How do we know? Well, what if 4 is not in my domain? That's that trick question again. And we need to know the domain before we can answer, right? Yep, I'll do that to you guys multiple times because I want to make sure that we really remember to ask about the domain, right? So in this case, where the domain consists of all real numbers, so now if it consists of all real numbers, then what? It's true, right? You only need one case, right? 5, 6, 7, 8, 9, all those work. There are plenty that are less than 3, but that doesn't matter because I'm only claiming that just at least one is true. Okay? True. How about this one? Let Q of x denote the statement x equals x plus 1. What's the truth value, Amanda, of that statement? It's tricky. I heard a false. What do you guys think? Beck's shaking his head no also. Yeah, because now this gets tricky because we have programmer brains, right? In the programming world, this is an operation, right? That means increment the counter x. But in the math world, that's an impossible statement. X cannot be equal to itself plus something else, right? So this is false, okay? You have to separate those two brains sometimes, right? Okay? Does it hurt? I hear some groaning a little bit over here. Oh, it's going to get so much worse. But it's awesome. Okay, so next up, what's the truth value of this? You have a question, Isaac? Oh, I saw your hand moving out of my peripheral. No, you're good. You are allowed to scratch. It's okay. All right. So what's the truth value of that statement if P of x is the statement x squared greater than 10 and the universe of discourse consists of positive integers not exceeding 4? Kim, I'm going to let you take a stab at that one.
So 4 is in the domain, right?
Yes. Yep. Yeah, 1, 2, 3, and 4. So, yes. Why is it true? Yeah, so 1, 2, 3, 4. And we're saying that at least one. Well, we know that one is one of the ones that's over. It's the only one in this case. So this one is also true in this particular scenario because there's exactly one, right? Okay? See, I always put these in the slide. I wrote them out for you already. Domain, we got the domain. And so again, no, this is important that this came up. So this proposition much like the universal where it's a conjunction of everything in the domain, this is a disjunction of everything in the domain. So remember our domain here, 1, 2, 3, and 4. Well, I'm claiming that P of 1 is true, or P of 2 is true, or P of 3, or P of 4. That at least one of those is true. And multiple can be true for an or statement to be true. Good? Okay? All right. There we go. True. Uniqueness quantifier. Once again, it means exactly one is true. All right. Let P of x be the statement that x minus 1 is 0. What is the truth value of this? Brady.
True.
You fell for it.
Oh, yes, I did.
That's all right. Oh, man, I left it off myself. I fell for it. Yeah. Yeah, I forgot to put it in there. See? It's easy to forget. The question is, you got to know what the domain is, right? So don't feel too bad because I fell for it myself, apparently. I forgot to put it in the slide. Yeah, but depending on the domain, and we're just going to go with a domain where it becomes true, right? Put the domain of whole numbers or whatever, okay? Sorry about that. Oh, man, bummer. Okay, other quantifier syntax, and this is going to get to your question that you had a second ago about how do you put them together, right? How do we express domains? So we can say let P of x be the statement x minus 1 equals 0, and we would ask what's the truth value of this? Well, we can also write this as, instead of saying P of x, we can just say P x minus 1 equals 0. I'm putting the function in the parentheses itself. So I don't have to have two separate declarations. Okay? That make sense? Good? Sure? Okay. All right. So another way we can do this now, this is where we're getting to what a domain looks like. And this is probably what you were talking about. And was it a calculus or discrete math? Discrete math, yeah. So look at this statement here. This statement has the domain and the function and everything all wrapped into one. I don't have to say let P of x equal blah, blah, blah. I don't have to say the domain of discourse is x, y, z. I don't have to do any of that. It's all in that one statement. So by looking at that, Caleb, what is the domain? What do you think?
Anything greater than 0?
Yeah, anything
Or, sorry,
less than 0, yeah. So the domain is all numbers less than 0, right? Okay? And what is the predicate? Yeah.
Real numbers, integer numbers?
Anything that's less than 0. If chicken was less than 0, it'd be in that domain. Anything less than 0, yeah. Yep. So, if that's the domain, what's the function here? Nate, what's the function?
X squared is greater than 0.
Yeah, so in other words, another way to write this very thing is like this. And we'd say P of x, let P of x be the statement that x squared is greater than 0, and the domain is everything less than 0, right? That's another way. All this crap is the same as that. Okay? So this is a very concise way to write it. Oftentimes when you're writing a proof, you start off with some big, long, nasty sentence or sentences or premise 1, premise 2, premise 3, and therefore conclusion number 1. You turn those sentences into equations that look like this, and then you run them through your proof process, which we'll learn another time. Okay? So this kind of syntax is very useful. So in English, what we're saying here, is the square of a negative real number is positive. Okay? That's what we're saying. You guys agree with that? So this is an example of a big, long, lengthy sentence in English that can be summarized in just a few little things if you know how to read it. Anybody here read music? Okay, I can't, so I might be using the worst analogy right now. I don't know. So, but I imagine if you look at music, something simple, not super complicated, you can maybe even hear it in your head a little bit. Is that true?
Like
If you,
the
the lyrics. Yes. But I mean, can you look at it and you can hear, you know the tone of the beat or the rhythm or the whatever it is? I'm totally musically ignorant. I don't know anything. Yeah. So when you look at let's look at one that we probably can all relate to, which is code. We look at something, your first day as a coder, like before you took 1400 or whatever, and you saw this stuff, you're probably like, what is this? But now when you look at it, you can go, oh, I know exactly what's going on there, right? If you're a chess player, after a while, you start not just seeing individual pieces, you see patterns, and you see, you can see strategies, and you see bigger things. It's just like, bless you, just like when you're learning to speak English, when you learn to speak whatever language you speak, at first you have to learn A, B, C, right? You have to learn the alphabet. And when you're first pronouncing a word, you have to sound out every letter of the word, right? But eventually there comes a time where you look at that and you just know what it is. You don't have to sound it out. You don't have to think about it. That's what's going on up here, okay? This stuff up here. Right now we have to kind of sound it out. Eventually we'll just look at it and know how to read it. It just takes time, okay? Mathematically, we're saying this. Now this is messy here, guys. Let's look at what's going on here. Remember our domain, okay? We're saying it's just numbers. We're just saying numbers. But I'm saying for all x, how do we read these kind of statements here? Right, how do I read this part? What am I looking at there? Yes, we have a p, therefore q, don't we? Right? So I'm saying for all x, if x is less than 0, therefore x squared is greater than 0. Dig it? I'm just teaching you how to speak the language here, folks. All right. Example number 2. For all y not equal to 0, and that is not the proper syntax for not equal to. I should have changed that, sorry. In our world, we don't do that syntax. In the discrete math world, the actual syntax for not equal to is that, okay? I did that because there's no key. This was originally I had typed up in Word for my printout notes, and I copied and pasted some of it into Notepad, and I forgot to change that one. Because in PowerPoint, you can actually make the little cool equations, but just don't use that syntax. Use this. If you see me doing it, it's because there was no way for me to easily type this not equal sign, all right? That aside, for all y that's not equal to 0, y cubed is also not equal to 0. Okay? That's what that's saying. You agree with that? I'm not asking if it's true. I'm just asking if you agree that that's what it says. Okay? What is that saying in English?
The cube of any number that isn't 0, for any number that isn't 0, its cube also isn't.
Yeah, any number cubed, unless it's 0, will not be equal to 0 when you cube it. Yeah. The cube of every non-zero real number is non-zero, right? That's what you said. Okay. What's this look like in an equation here? Okay, it's the same idea. We have for all y, if y is not equal to 0, therefore y cubed will not be equal to 0. How's your brains doing, guys? Okay, don't worry. I'll hurt them. This is my goal. All right. Now, this is interesting, okay? I'm just going to read it because it's written well. This is right out of the book. The restriction of a universal quantification is the same as the universal quantification of a conditional statement. That's what that note in purple, or that math thing is saying there, okay? The restriction of this universal statement is the same as the quantification of a conditional statement here. You can, in other words, you can do them both ways, okay?
Just to make sure that I understand, the restriction of universal quantification, that's the part where you got the not equals to 0.
Yes, yeah, the domain restriction, yeah. Yep. Yeah. Okay, other questions? Okay, this one. How do we say this one, Isaac? What do you think?
Like there's at least one value greater than 0, or z squared equals 4.
Yeah, there exists some value greater than 0 such that that value squared is equal to 4, right? Very good. Okay. What are we saying in English? It's Pretty simple.
There's just a positive number, that if you square it, it equals 4.
Yeah, what does that mean? 4 has a square root, right? That's what we're saying, right? Okay, there is a positive square root of 4. Okay, that's what we're saying. Make sense? Fancy way to write that. Mathematically, again, we're saying, now this is a little different. This is not a conditional statement. We're saying there exists some value z that such that z is greater than 0, and when you square it, it equals 4. Okay? Not a therefore like the universals. And we have a similar statement here that the restriction of an existential quantifier is the same as the existential quantification of a conjunction. Okay? That's, in other words, that is the same as that. That's all that fancy sentence says. This stuff becomes critical when, and I keep talking about proofs, and we'll get there. And if anybody's taken my HTML class, the first maybe 3-4 weeks of the class, I kept saying, wait till we get to CSS, wait till we get to CSS, everything will be awesome. This is the same thing here. Wait till we get to the proofs, and all this stuff will fall into place, why this stuff matters. But I'm teaching you and exposing you to logical equivalences and things that mean other things, so that when you see them, you can start reducing them and be able to make your proof, make your case. Okay? Now, the order of precedence for quantifiers is higher than everything. The other day, we looked at the order of precedence, and this is what we looked at, right? Well, quantifiers is bigger than that. Okay? So quantifiers are first, not bigger, but they're first. And then negation, then conjunction, disjunctions, then conditionals and biconditionals. All right, somebody was asking about scope earlier. Can't remember. But we're going to talk a little bit about variable scope here. So I haven't told you what these terms mean here, but I want to see if you can sort of intuit what they mean. So just anybody, because I haven't told you what this is, I don't want to single out anybody. Okay. What variables are free and which ones are bound, if any? Yeah. Yeah, x is bound, and x is bound right there. Y is free because there's nothing, no quantifier talking about it. So y can be anything. Right now, we don't know what it's going to be, but it could be anything. Okay. All right. So, how about this one? Which variables are free? Which variables are bound? This is one of them trick questions that I told you I'd do in class. Say again? I'm not going to confirm nor deny what you just said, but I will tell you there are 2 variables that are bound. Interesting. You ready? Let me tell you what they are. The man is like, no, don't you dare tell me. I think I like what you're saying. I didn't quite hear it, but it sounds like you got a working theory. Go for it.
I was just saying because this one has a existential, and this one has an all variable. It doesn't have anything with it, so that was free because it doesn't have anything.
So you're barking up the right tree here. There are 2 variables that are bound. The first one is x. The second one is x. Told you, it's a trick question. Okay, here's why. This x binds these 2 x's. That x binds that x. This x is not in the same domain necessarily. It's not the same x. Okay? Now, we've seen this problem before in Java. Right here. Look at this. We know how to read this code, I hope. Okay? We have this variable called color right here. This is the class level variable. And then we have the function level variable right here called color. And we have to say this, meaning this one, is equal to this one, which is that one there. Okay? What's a better approach for that? If you've taken my 1410 class, you know what my better approach is. Use different names. Use better names, right? Something like that. Then it's absolutely clear, it's unambiguous. So, going back to this other thing here, use different names. Okay? Now, if you're using the same domain, then sometimes it can be hard to use different names. But that's an approach that you can take. Think about your equations and see if you can make them a little bit more clear, a little bit more easy to read. Sometimes you can't. Sometimes you're stuck with something like this, and that's okay. All right? All right, here we go. Let's take a little bit more deep dive into this. Let P of X be the statement that X has taken a course in calculus. The domain is students in this class. Okay? How would we pronounce this?
For all students in this class, each student has taken a course in calculus.
For all students in this class, each student has taken a course in calculus. Very good. Okay, that's correct. How do you negate it?
There's at least one student that hasn't taken calculus in this class.
That's how you would. So that's how you would say the negation of it. But how do you negate the formula? Yeah, you can just draw a line over it, right? Or you can do the other operation, which is this little guy right in front of it, right? Okay. We'll just draw a line. Okay. So this is what it looks like negated, right? Now, you started to make a statement here that is that one right there. That is also the exact same thing. So here I'm saying this. We originally said for all students in this class, every student has taken a course in calculus. This is saying it is not the case that all students in this class have taken a course in calculus. If that's not the case, then what does that mean? At least one person in this room has not taken a course in calculus. Isn't that what that's saying right here? There exists some student X such that it is not the case that they have taken a course in calculus, right? Which is exactly what you said a second ago, okay? Well, believe it or not, we just applied I thought I had a note that said it. We just applied De Morgan's law on this, okay? We'll talk about how that works in a minute, but we just used De Morgan's law. Okay, another one. Q of X has taken a course in calculus, same thing. The domain is students in this class. How do we pronounce that? Yeah, there's at least one student in the class who's taking calculus, right? Good. How do we negate that? Kim, how do we negate it? Not how do we say it, but just how would we turn that into negative? Yes, for those watching the video, she's drawing a line in the air. Okay, yes, like so, all right? Now, again, we're claiming that in this scenario that's circled, it is not the case that at least one person has taken a course in calculus in this class. That's what we're claiming with the negation of it, right? In other words, for all students, it is not the case that anybody's taken this course. That means nobody took the course, right? We applied De Morgan's law here to get that, okay? And here is De Morgan's law for quantifications. Notice, this is what we just saw a second ago. This becomes that when you apply De Morgan's law. Okay? This is also in your book. So how do we apply it? What's the rule? How does it work? I have to see if this is a slide where I wrote it out or if I get to write it on the screen for you. Yeah, okay, there we go. Move the line and flip the sign. The other day we talked about break the line and flip the sign. This case, we're moving the line and we're flipping the sign. Okay? Now this time, let's stop. Everybody, I know you're probably taking some notes. For just a minute, I want you to hear what I'm about to say. The original De Morgan, when we had, I'm going to go back one so I can have room here. When I had something like P or Q negated, and we said break the line and flip the sign, what did break the line mean? It meant break the line, and it meant flip that sign, right? Well, in this case, when I'm talking about flipping the sign, I'm talking about going from existential to universal or vice versa. That's what I mean in that case, all right? Oh, that's fun, that it stays there. That's an interesting feature, okay? All right, so take a look at what's happening here. In this particular case right here, I moved the sign, to right there, or moved the line, I should say, and then I flipped the sign and it becomes universal. That's all we did. Move the sign, move the line, flip the sign. Move the line, flip the sign. Okay, now we've applied to Morgan's law. So I've said this a few times, but I want to ask you guys, why do I care? Why do we care? Why do you care about something like De Morgan's law, something about a propositional equivalence? Why a logical equivalence? Why does this stuff matter?
Because they're running things that are worded such that it's kind of nasty to think through, and through these things you can put them around.
These kind of things can help you reword things, simplify things, make them easier to understand. And again, ultimately when you're dealing with a proof, you have English sentences that first step, you turn into formulas like this. Next step, you're saying, I'm claiming that if these sentences are true, that this thing over here will exist. So if these sentences are true, something else will exist. Well, I'm going to mathematically prove that. I'm going to try to manipulate these things mathematically to make them look like the thing I'm trying to prove. And the only way to do that is with this kind of manipulation. Okay, good. All right, what is the negation of each of the following statements? There is an honest politician, and all Americans like cheeseburgers. What is the negation of those statements? There's two separate, unrelated statements. There are no honest politicians, and that is not correct. Oh, tofu, nasty. Although I do like it in hot and sour soup. There you go. At least one American does not like cheeseburgers. Or not all Americans like cheeseburgers. Both of those will work, right? Okay? Questions about that idea?